we know, but we will study today that matter will also have the wave nature. That is given by the Davison and Germer experiment. But this Davison and Germer experiment is removed now from your syllabus. So we will not go in detail of the Davison and Germer experiment. I will only tell you the basics of Davison and Germer experiment. What they did in Davison and Germer experiment, uh, they have find it out that electron also shows the diffraction, and diffraction is a phenomena of wave. So they said that electron shows the wave nature also, and electron is particle. So every particle shows the wave nature also. This is proved from this experiment. So matter shows the wave nature also. This we will see. We will see the de Broglie hypothesis today. Okay, so I am starting. First of all, we will discuss the photocurrent and the stopping voltage. Photocurrent and the stopping voltage. Now, what is photocurrent and what is stopping voltage? First, we will discuss the photocurrent. Suppose you have this vacuum chamber like this. This is a vacuum chamber, and these are the metal plates. These are metal plates. These are metal plates, and these metal plates are connected with battery and a rheostat system. Battery and rheostat system. And what is happening? Suppose radiation of light is coming, an incident on the metal. Okay, this is the radiation is coming. Radiation is coming. Okay, so radiation is coming, an incident on the metal plate. Okay, incident of the metal plate, and we know that radiation is made up of photon. Radiation consists of photons. So basically, photons are coming. An incident on the metal plate.
Yes.
Yeah. So what will happen? This is the metal plate, and on the surface of the metal plate there are free electrons. Now photons are striking with the free electrons. So there will be the ejection of the free electrons. There will be the photoelectric effect. Means electron will be ejected from here. Electrons will be ejected like this. Electron will be ejected. Suppose this plate is cathode. This plate is cathode, and this is also known as emitter. Why we are saying emitter? Because electrons are emitted from this plate, and this plate is known as anode. So cathode I will represent with C, anode I will represent with A. So this plate is anode, and this anode is known as the collector. This anode is known as the collector. Now electrons are, because you can see here, this is the positive side and this is the negative terminal of the battery. So this will have the negative potential and this will have the positive potential. So basically electron will move from the positive negative potential to the positive potential, means electrons will move from cathode to anode. Electron will move from cathode to anode. Okay. Now electrons are emerging or emitted by the incident radiation from the cathode, and these electrons are moving towards anode. Okay, these electrons are moving towards anodes. So what will happen? Electrons are moving. So due to these electrons are photoelectrons. These electrons are photoelectrons. Now I told you that whenever uh, due to the incident radiation, there will be the ejection of electron. Those ejected electron will known as the photoelectron. So these are the photoelectrons, and photoelectrons are moving towards the uh, means towards the anode from the cathode. So due to the motion of the electron is a charge, and motion of the charge will generate electric current. So now electrons is moving. So due to the motion of the electron, there will be current. There will be current. Okay. So electron will move like this. So from the emitter, electrons are ejected. So these electrons will move toward anode, and from anode, these electrons will move like this. It will be move. It will move like this. Okay. And finally, it will move like this. And finally, the electron will be here. So due to the motion of the electrons, there will be current, and that current is known as the photo current. That current is known as the photocurrent. Now see what is photocurrent. Photocurrent, the current due to the photoelectrons emitted by cathode is called photocurrent. Okay, the current due to the photoelectrons emitted by cathode is called photocurrent. After that, what will happen? Due to this radiation, okay, here from this metal plate, there will be the ejection of electron. Here, there will be the large number of electron. Okay, there will be the collection of large number of electron. So now, due to that, now what will happen? Due to that, what will happen? It will be like that, like on the road, there are so many cars at the same time. So there will be jam there. So here is the electron jam. So due to the large number of electron here, electron will not move properly towards the anode because here are large number of electrons. Because here are electron jam, the space charge problem. Okay, here there is charge or more charge here. So due to that, what will happen? Uh, due to the more number of electron in this region, the electron will not go properly towards the anode. Due to that, there will be less photocurrent. There will be less photocurrent. So to solve the problem of the space charge, this is known as the space charge. Okay, because here there will be the accumulation of electron. So to solve this problem, what we will do, we will give this plate as positive charge. Positive charge. Or to this plate, we have given the positive potential. Due to that, due to this positive potential, now here is the positive potential. Now electron will be attracted towards this plate. Okay. So now you have given the positive potential. Due to that, a force will be on these electron in this direction, and now the electron will move very fast. And due to that, there will be more photocurrent. There will be more photocurrent. So you can see here space charge, the negative charge in the region between cathode and anode. Negative charge, okay, this charge between the region cathode and anode due to large number of photoelectrons, due to which low photocurrent. Okay, because of the there are so many electrons, it will look like there are so many cars on the road and there is a jam there. Now what is the solution? Increase the positive potential on anode. If you will increase the positive potential on anode, smoothly the electron will move from cathode to anode and there will be increase in the photocurrent. Okay. After that, you have given the positive potential. Now electron are moving from cathode to anode easily, and there will be more photocurrent. Photocurrent will increase while you are giving the positive charge to this plate. Suppose you have given the negative charge to this plate. Suppose you have given the negative charge to this plate or negative potential to this plate. So what will happen in that case? If you will give negative potential to this plate will repel electron. This plate will repel electron coming towards this plate. So what will happen? These electrons have the kinetic energy. I told you that radiations are incident on the metal surface. Okay, some energy will be spent to overcome the work function of the metal surface, and remaining energy will be the kinetic energy of the electron. So electron will have the kinetic energy. Due to that, the electrons are moving in this direction. But you have given now the negative potential. You have given the negative potential. Due to that, what will happen? This electron will be repelled in this direction. In this direction. So there will be a time when you will increase again and again. You are increasing the negative potential on this plate. There will be a time when no single electron will move to anode, will reach to anode, you can say. The negative potential becomes so large so that no single electron can reach the anode, and that negative potential is known as the stopping potential. You can see here. On increasing the positive potential, we know anode with respect to cathode. On increasing the positive potential on anode with respect to the cathode, more and more electrons are attracted towards anode. More and more electrons are attracted towards anode. Okay, because if you will give the positive potential to this plate, more and more electrons will be attracted because this is positive charge and here is the negative charge. Okay. After that, towards anode, and photocurrent increases. Obviously, the photocurrent increases, okay, because the motion of the electron will increases until it reaches to the saturation value. After a certain period of time, if you will now see, you are increasing the positive potential this time. You are increasing the positive potential on this plate. So what will happen? More and more electrons, more and more number of electrons will reach anode due to this positive potential. Okay. After a certain period of time, here there will be no electron to reach there, because all the electron will already reach to anode, because incident radiation is same. Incident radiation is same means number of ejected photoelectron will remain same, and you have increased the positive potential as much so that all the electrons are reached to anode already. So now there will be no increase in the current, photocurrent. Photocurrent will increase, but after a certain value of the positive potential, photocurrent will have some saturation value. It will not increase after that. Why? Because number of photons will not increase. After that, what I told you, applying negative potential on anode. Now we are applying the negative potential. So what will happen? Due to the negative potential, electron will be repelled, and there will be a particular value of the negative potential, so that no electron, not a single electron will reach towards the anode. If we apply negative potential on anode with respect to cathode. So keep this picture in your mind. Keep this picture in your mind. This is anode, this is cathode. So electrons are moving from cathode to anode. If we apply a negative potential on anode with respect to cathode, photoelectrons are repelled by anode. Okay, because for anode is now have negative potential, that is why anode is repelling the electron. Photoelectrons are repelled by anode, and photocurrent will decrease. Obviously, the photocurrent will decrease when the electron will be repelled. Motion of the electron will be reduced, so the photocurrent will decrease. On further increasing negative potential on anode, A means anode, a saturation arises when no electron can reach at anode and photocurrent becomes zero. So there will be a particular value of the negative potential on this plate so that the photocurrent will become zero because no electron will reach towards anode, will reach to anode. That is known as the stopping potential. The minimum magnitude of negative potential on anode with respect to cathode, which can just stop the photocurrent, is called a stopping potential or voltage. Stopping potential or a stopping voltage. Now you can see this graph. This graph is basically like this, okay? So I have drawn like this. So this I is the photocurrent. So photocurrent versus anode potential with respect to cathode. So if you will increase, the voltage or positive voltage here in this is the positive voltage and this is the negative voltage. If you are increasing the positive voltage, so first the potential will increase. No, not the potential. The photocurrent will increase, but after a certain value of positive potential, after suppose this value of positive potential, the current will become constant. Photocurrent will become constant because number of photons will not increasing. But if you will give negative potential to the to anode, now you are giving a negative potential. After a certain value, there will be no current here. The photocurrent becomes zero, and this is known as the stopping potential. This is known as the stopping potential. Stopping potential or the stopping voltage. So this graph is something like this, okay?
Okay.
Okay, so once again, I'm explaining one by one. This is the metal plate. This is also a metal plate. This is a vacuum chamber. Vacuum chamber means there is no particle inside this chamber except electrons. And this system is connected with the battery and rheostat. So with the help of battery and rheostat system, we can either increase the negative potential here or either decrease the negative potential. Means we can just change the polarity of the system. Okay, by the way. So now radiation is incident on cathode here. On this plate, radiations are incident. So due to the radiation, what will happen? Photoelectric effect, electron will be ejected out. So electrons will be ejected out. So these electrons will be ejected out and these electron will go towards anode. Okay, initially the anode is positively charged. Initially the anode is positively charged. So that is why the electrons are going towards anode. But what will happen? Here will be a problem of space charge. Charge will be accumulated here. More number of electron will be there. Like more number of vehicles on the road. So that there will be jam like, okay, means if there are so many vehicles on the road, so can you move? No, like this the electron cannot move because of the space charge. So to solve this problem, what we will do, we will increase the positive potential. If we will increase the positive potential, then automatically electron will be attracted towards anode. Now more and more number of electron will be attracted towards anode. Due to that, the photocurrent will increase. But after a certain value of the positive potential, the photocurrent will become constant. Why? Because number of photoelectrons are constant. Number of photoelectrons are depends upon the intensity of radiation. But radiation is constant. Intensity of radiation is not changing. Number of photons are same. After that, suppose if you are increasing the negative potential on this plate, so electron will be repelled, and there will be a certain value of the stop negative potential on anode, so that no single electron can reach anode. And in that case, the photocurrent will become zero. Why? Because no electron are reaching towards anode, reaching to anode. There will be no current. If there will be no current, then that value of the negative potential is known as the stopping potential. Okay, you can take the screenshot.
Done.
Nawal, done?
Yes, sir.
Okay. So basically this is cathode emitter, because electrons are emitted from cathode. Collector, because electrons are finally collected at anode. Write down this. Take the screenshot. Done?
Yes.
Okay. Take the screenshot. Scroll down.
Yes.
Yeah. Okay. Okay. So see this graph. This graph is like this. Okay. So you can take the screenshot. Now we will derive the expression for the stopping potential. Okay. Okay. Derivation for stopping potential. This is cathode. This is anode. Cathode, anode, electrons are moving from cathode to anode. Radiation are incident on cathode. Electron are emitted from cathode and moving towards anode. So I have drawn cathode and anode, and electrons are moving, and these electrons will have the kinetic energy. Obviously, these electrons will have the kinetic energy. What you are doing, electrons are emitted from here, and you are increasing the negative charge. You are increasing the negative charge on this plate. Okay. So when you are increasing the negative charge, so this is negative charge and electron is also negative charge. There will be an electrostatic force of repulsion. Hmm? So electrons, something is moving like this. Something is moving like this, and that this thing that is moving feels some repulsion in this direction. So this body will have to do some work to move forward. Obviously, suppose there is a force that is in this direction and you are moving in this direction, so you have to move. For moving in this direction, you have to do some extra work. So electron will do the work to move in this direction. While moving from cathode to anode, electron has to do work against electrostatic force, against electrostatic force. Okay, so electron will have to do some work because of the repulsion from the anode, and this work done by the electron at the expense of the kinetic energy of the electron. So kinetic energy of the electron will reduce, and where that kinetic energy is going, where that energy is going to do the work to overcome repulsion. So you can write electron has to do work against electrostatic force of repulsion on the expense of its kinetic energy. Okay, kinetic, initially the electron will have kinetic energy, but electron is doing now work. So to do work, energy will be expended. Now suppose you are increasing the negative potential, increasing. So there will be more repulsion to the electron, Now you have increased the value to the stopping potential V naught. So what will happen? This the potential of this anode becomes so much that not a single electron can come to anode. Means the electron will have the maximum kinetic energy. That electron also cannot come to anode. Okay. So you can write at stopping potential, even the fastest electron, fastest electron means the electron which is having maximum kinetic energy. At a stopping potential, even the fastest electron cannot reach anode. And photocurrent becomes 0. Photocurrent becomes 0. That is the story now I told you. Okay. So you can say that suppose this electron will have the maximum kinetic energy. So the maximum kinetic energy of the electron is expended in doing work done against the electrostatic force. Okay. And we know that work done can be written as charge into potential difference, charge into delta V from the electrostatic. I don't know whether you know this or not. So work done is charge in terms of the potential difference. Work done is charge into potential difference. So how much work the electron have to do? Charge of electron multiplied by the potential difference. Potential difference is V naught. So maximum kinetic energy of the electron will be equal to E into V naught. E is the charge on electron, V naught is the stopping potential. So you can say V naught is equal to maximum kinetic energy of the electron divided by E. divided by E. This can be one formula. V naught is the V naught is the stopping potential. Now further you can simplify this. You know that maximum kinetic energy of the electron is given by energy of photon E minus work function of the metal surface, and this is Einstein's photoelectric equation. So put this value here. So maximum kinetic energy, you can write V naught. That is maximum kinetic energy by E. Maximum kinetic energy is E minus phi. You can write E minus phi by E. Okay. So it is V naught. E can be written as hc by lambda. So you can write it as E is equal to hc by lambda E minus phi by E. So this is another formula. E is hc by lambda. H is the Planck's constant. C is the speed of light in vacuum. Lambda is the wavelength of the incident radiation. Okay, so you can write this V naught hc by E 1 by lambda minus phi by E. Now y is equal to mx plus c. It will be mx minus c. So graph of y is equal to mx minus c is this. This is the graph of the straight line having the equation mx minus c, and this is the intercept c, and this tan theta is the slope. M is the slope of the graph. Okay, you should know this. So, and now we will draw the graph between the stopping potential and 1 by lambda. The stopping potential and 1 by lambda. So y is equal to, this will be m, slope, and this is x, and this phi by e is the negative y intercept, means this. So this type of graph you will have. Okay. Stopping potential V naught versus 1 by lambda. So it will be a straight line like this. It will be a straight line like this. And slope of this graph will be m, and m is this hc by lambda. If this angle is theta, then slope is also given by tan theta. Okay, and what is this value? This value will be this phi by e. So basically this value will be 1 upon lambda naught. Okay, so one more thing. You can see the formula for the stopping potential. See here. So stopping potential is V naught is the stopping potential, H is the Planck's constant, C is the speed of light, lambda is the wavelength of incident radiation, E is the charge on the electron, phi is the work function, E is the charge on electron. Now H is constant, speed of light is constant, E is constant. So potential, stopping potential is depending upon is a function of lambda and E. So you can write stopping potential is depending upon the wavelength of the incident radiation and the work function. Lambda and phi. V naught depends on lambda and phi. V naught depends on lambda and phi. What will happen if you will increase the intensity of light? Here in this case, for example, in this case, if you have increased the intensity of light, then what will happen? Photocurrent will increase or decrease? Can you tell me? Photocurrent will increase or decrease? Okay, photocurrent will increase. Why? Because if you will increase the intensity, more number of photon will strike on this metal plate, more collision between the electron and photons, more electron will be ejected out, means more number of photoelectrons. If more number of photoelectrons means more photocurrent. Now, stopping potential is depending upon wavelength of radiation and work function of the metal. But we are only changing the intensity. We are not changing the wavelength and the work function. So stopping potential will remain same. So you can see here. This thing I have written here. V naught can be written as SC by E lambda minus this. The stopping potential depends on the lambda of the radiation, work function of the metal, wavelength of the radiation or frequency. On increasing the intensity of the light, the number of photoelectron increases. Many times I told you, which increases the number of ejected electron, photoelectron, and hence photocurrent will increase. But energy of each electron still remains same. Hence stopping potential remains unaffected on changing the intensity of light. So in this way also you can say on increasing the intensity, the energy of the each photon will not change, means this E will not change on increasing the intensity, and phi will also not change. So this V naught will remain constant. In another way you can say stopping potential is depending upon wavelength of radiation and work function. Both things are not changing when you are changing the intensity of light. So this type of graph you will get. See, this is the graph between the photocurrent, and the anode potential. Okay, anode potential. So this is retarding potential, means negative potential. So this is the stopping potential. So first graph is like this. This have intensity I1. Second graph is like this. This have intensity I2. Third graph is like this. This have intensity I3. Now I3 here is greater than I2 is greater than I1. Now for this graph, photocurrent is this. For this graph, photocurrent is this. For this graph, photocurrent is this. So I1, I2, I3 means you are increasing the intensity. Photocurrent is increasing because more number of photoelectrons will be there. Understanding, Matthew and Nawal?
Yes, sir.
Yes, sir.
Okay. So take the screenshots.
Done.
Okay. So this chapter will also be finished today. This is finished. Now we will discuss the wave nature of matter. Wave nature of matter. This is the question appeared in board. Drive an expression for the stopping potential from Einstein photoelectric equation. So you can do this. Okay, this is the expression for the stopping potential and with the use of the Einstein photoelectric equation. So I think you can do this question. So I want to show you means how in your board exam the question can be asked. Wave nature of matter. Matter is also having wave nature. So basically in 1905, photoelectric effect discovered which proves the particle nature of light. So light has particle nature. So light shows wave nature we know, we already knew before 1905 also we knew that light is having wave nature because light shows the interference, diffraction and polarization. Interference, diffraction and polarization are the phenomena of wave. That is why light is having wave nature. But when photoelectric effect is proved, so we were sure at that time that light have the particle nature also, apart from the wave nature. After that, particle nature of the light is proved by the Compton effect. There is one Compton effect. There is one black body radiation. These effects are showing light is having particle nature also. But then there comes a scientist named De Broglie. Then there came a scientist, De Broglie, said that nature has symmetry. Said that nature has symmetry and gives his hypothesis, De Broglie hypothesis. Okay, so this is all about the wave nature of the matter and radiation. So a scientist, De Broglie, actually he was the PhD student De Broglie. So he said that nature has symmetry. Means what is the meaning of this statement? If light is having particle nature, then matter will also have the wave nature. So he gives his hypothesis, De Broglie hypothesis. Every moving particle has a wave associated with it. Very good. So this statement is given by the De Broglie. I will explain this with the help of example. De Broglie hypothesis. Every moving particle has a wave associated with it. For example, if m is the mass of the particle and this is moving with speed v or velocity v, then momentum of the particle will be mass into velocity. Okay. Mass into velocity. And what De Broglie said, every moving particle has a wave associated with it. He has given this expression. Wavelength of the wave associated with particle is given by hy lambda. Hy p. What is h? Planck's constant. And this lambda is also known as the De Broglie wavelength. And this is momentum of particle. And lambda is the wavelength of wave. Wavelength of wave, also known as De Broglie wavelength. And Planck constant value is given by 6.626 into 10 to the power minus 34 joule second. And one more thing, always remember, every moving particle has a wave associated with it. if a particle is moving or anything is moving, suppose this object is moving, so there will be a wave associated with this, and that have the wavelength lambda h is by p, and the wave associated with it, there are many types of wave: electromagnetic wave, there are mechanical waves also. But he has given the name to this wave as matter waves. What are matter waves? Waves associated with a particle known as matter waves. Now, what example we will take? This example. Suppose this person having a mass of 100 kg and this person is moving. In normal life, we have this kind of can a person have the mass of 100 kg? No. Okay, let's suppose person is having, or this object, you can take this as an object, or this object has the mass of 10 kg and moving with a speed velocity of 10 meter per second. So now we will calculate the de Broglie wavelength of this wave, this particle or this object. Okay, because de Broglie said that for every particle the wave is associated. For every object the wave is associated with. If this person is moving, then there will be the wave associated with this also. So we will calculate the wavelength. So how we will calculate the wavelength? Lambda wavelength is given by h divided by p. Wavelength is given by wavelength associated with this object is h by p, given by de Broglie h by p. Now h is Planck's constant, and momentum of something which is having mass m and velocity v, m into v. Okay, it will be mv. So Planck constant is 6.626 into 10 to the power minus 34 joule second, divided by mass is 100 kg and speed is 10. So if you will calculate this you will get the wavelength 6.626 into 10 to the power minus 37 meter. Okay, so you will get the value of lambda, that is equal to 6.626 into 10 to the power minus 27 angstrom. See this wavelength associated with this, very small. That is why when some object, heavy object is moving, there is a wave associated with that, but the wavelength of that wave is very small, so we cannot detect that wavelength. Okay, so lambda is very small, cannot be detected. Okay, now instead of this, suppose an electron is moving, having a mass m, velocity v. So if the electron is moving, something is moving, then waves are associated with it, and we can calculate the wavelength. Lambda is equal to h by p. Lambda is equal to h by mv. H is 6.626 into 10 to the power minus 34. Mass of the electron 9.1 into 10 to the power minus 31 kg, multiplied by, electron is a particle, very small particle having large speed of 10 to the power 6. When you will calculate, so lambda will come out to be 7.33 into 10 to the power minus 10 meter, and it will be approximately equal to 7.33 angstrom. Now this wavelength is significant. This wavelength is significant. Means if the electron is moving, then wavelength of the wave will be significant. Wavelength of the wave will be significant if electron is moving. because electron is very small particle as compared to this person. So we can say that for electron, Davison and German experiment, they have proved the wave nature for electron. Okay. So if electron is moving, so wavelength of the wave will be significant. Understanding?
Yes, sir.
So now we will see the de Broglie wavelength in terms of the kinetic energy. Okay, in terms of kinetic energy, we will see. A mass m is moving with velocity v. So if a mass m moving with velocity v, it will have the kinetic energy half mv square, and it have the momentum mass into velocity. From here you can find velocity, that will be p by m. Now put this value of velocity here. So you will have the kinetic energy half m v square, means p square by m square. From here m and m will be cancelled out. So you will have p square is equal to 2mk. So momentum you will have under root of 2mk. K is the kinetic energy. So what is the wavelength? H by P. So wavelength in terms of the kinetic energy, H divided by 2mk. So remember this formula also. Wavelength, de Broglie wavelength is H by 2mk. This question. An electron, this is very famous question. An electron, alpha particle and proton has same kinetic energy. Same kinetic energy, okay? Arrange them in order of decreasing de Broglie wavelength. Now you have formula of de Broglie wavelength. Lambda is equal to h upon under root of 2m into k. Now h is constant, 2 is constant, kinetic energy is also constant. So this lambda will depend upon the under root of mass. Now more mass, less wavelength. So alpha particle, this alpha particle is basically the helium nucleus. If you will remove 2 electrons from the helium, you will get an alpha particle. So alpha particle will have the 4 AMU mass, maximum mass. So the alpha particle, lambda of alpha particle will be least. After that, the wavelength of the proton, and after that, maximum wavelength will be of electron. Because mass of electron is less as compared to the mass of proton, and mass of proton is less as compared to the mass of alpha particle. One more question will solve. Establish a relationship of de Broglie wavelength lambda associated with a particle of mass m in terms of its kinetic energy. So You can establish the relation now in terms of the kinetic energy, de Broglie wavelength. So this question is of board's exam. You can do this. Now de Broglie wavelength in terms of the stopping voltage or a stopping potential. Suppose this is a charge Q and this charge have the velocity V. Okay, V is the velocity and this V is the potential difference, potential. Now this charge is having some kinetic energy and this charge is moving from here to here. Charge is moving from lower potential to the higher potential. If charge will move from lower potential to the higher potential, it will have to do some work and that work will spend the kinetic energy of this charge. And we know that work done can be written by Q into delta V. And here work done by the charge will be Q into V. So you can write work done is on the expense of kinetic energy. The work done is on the expense of kinetic energy. Initially, this charged particle is moving, means it will have some kinetic energy, and this charged particle is moving from lower potential to higher potential. Naturally, the charged particle moves from higher potential to lower potential, but this is not natural. It is moving from lower potential to higher potential. So you have to do some work, means charge have to do some work, and that work will spend the kinetic energy of the charge. So you can say kinetic energy of the particle will be work done, and that will be equal to Q into V. So kinetic energy will be Q into V. So what is the wavelength? Wavelength is given by wavelength of this particle will be h by p, and in terms of kinetic energy it will be 2 mk. And what will be the value of kinetic energy? Qv. So this will be in terms of the accelerating potential. In terms of the potential, the wavelength of the wave is h divided by under root 2m qv. Now, if suppose this charge is electron, and electron is moving from here to here like this. Electron is moving. We know h is the Planck constant. Me is the mass of electron, that is 9.1 into this, and charge of electron is this. We can calculate the wavelength of electron. For charge, this electron is moving, so kinetic energy of the electron will be work done. Kinetic energy of electron is equal to the work done, and work done will be charge into potential. Okay, so lambda of electron, wavelength of the electron motion, is h divided by under root 2 mk. H is the Planck's constant. It will be 2m. K can be written as EB. So H is 6.626 into 10 to the power minus 34 divided by under root of 2 m, mass of electron m. We have 9.1 into 10 to the power minus 31 kg. Charge on electron 1.6 into 10 to the power minus 19 multiplied by V. When you will calculate this whole value, you will get under root of 150 divided by lambda, and under root of 150 can be given by 12.27 divided by under root v. Oh, sorry, this is v. So for electron, this formula you have to remember. If electron is moving, then wavelength of electron will be this. And if any charge is moving, then wavelength is this. If charge is moving to this potential, then wavelength is this. Okay. Before that, we will solve one easy question. Find de Broglie. Okay, first note down, then we will solve. Okay. Hello, Nafisa, how are you?
Hello, sir. I'm fine. How are you?
I'm good. Okay, so all of you, please take the screenshot. Then we will solve question.
Done.
Okay.
Yes, sir. Done.
We will solve now this question. Just try this question by yourself. And in this question, this formula will be used. We know that if a charged particle is accelerated through some potential, and wavelength associated with is given by under root 2m charge, and the potential through with the charged particle is accelerated. Try this question. You have 3 minutes. You have to find the value of x. This type of questions will appear in your exam. One more thing. One is proton and one is alpha particle. So for proton, you will take mass of proton as mp, and for alpha particle, you will take mass as 4 times of mp. One more thing. Charge on proton, you will take q. Charge on alpha particle, you will take 2 times of q. Okay.
So it's answer 64.
Matthew, Nawal, and Nafisa. Anyone got answer?
Yes, sir. Told I got
What?
64.
What?
64.
64. Okay. Okay, so they are asking the ratio between the de Broglie wavelength associated with proton accelerated through potential of 512 volt. So proton is there and this proton is accelerated to 512 volt. So wavelength associated with proton is given by h upon under root of 2m qv. Okay, so it will be h under root 2 mass of proton. You will take this mp. Charge on proton you will take q and accelerated through 512 volt. Now alpha particle, for alpha particle, an alpha particle is accelerated through x volt potential. So wavelength associated with alpha particle is h divided by under root 2m, 2 into mass of the alpha particle. Mass of the alpha particle is 4 times of mass of proton multiplied by 4 times of mass of proton. It is multiplied by charge on proton, charge on alpha particle, that is 2q. And for instead of this v, you will put x. You will put x. This is x, 2qx, and x you have to find. Now they are saying that ratio of is found to be 1. The ratio is found to be 1. So ratio of wavelength of proton and alpha particle is found to be 1. Is equal to 1. This is given. So if this is given, so you can say ratio wavelength of proton, you will multiply this in this side. You will get wavelength associated with proton is equal to wavelength associated with alpha particle, means this value is wavelength associated with proton, h divided by 2m qv is equal to h divided by this value, 4 to the 8 to the 16. Oh, it will be this value, sorry. It will be this value, wavelength associated with proton, and this is equal to wavelength associated with alpha particle, and for alpha particle the wavelength associated is this. So this will be equal to h divided by under root of 2 into 4 times of mass of proton multiplied by 2q into x. Now this h and h will be cancelled out. Under root and under root will be, you can remove under root. So you will have 2 times of mp. You will have this value. You will cross multiply this side. You will have this value, this value. You will take a square on both sides. So you will have this value. 2 into 4 times of mass of proton multiplied by 2q into x, that is equal to 2 times of mass of proton multiplied by q multiplied by 512. Now cancel, mp is cancelled with mp, 2 is cancelled with 2, q is cancelled with q. Okay, now it is 2 and this is cancelled with this, so it will become 2 to the 4, 2 5 the 10, 2 6 the 12. Okay, so it will be 4 and it will be 4 6 the 24 and 4 4 the 64. So x you will get 64. Right answer. Very good. Right answer 64. So this type of question you will get in your board exam. Now you can take the screenshot, and this chapter is finished. Dual nature of matter and radiation is finished, because if you will see here, Davison and Germer experiment is removed this time. So we will not touch this topic. But I told you that I will tell you what is in the Davison and Germer experiment. In the Davison and Germer experiment, two scientists named Davison and Germer proved wave nature of electron. They proved that electron shows the diffraction. Okay, take the screenshot, and in the next class we will start the atoms and nuclei, and as soon as possible we will finish the syllabus. Please take the screenshot.
Done. Answer.
Okay. Okay, all of you. Now we will meet in the next. We will meet in the next class